Microsoft Word.
Okay, today um we'll be looking at number theory today, but first of all, we're going to start with our warm-up problem, which we'll quickly do. We're going to start with our warm-up problem. Our warm-up problem for today's class is related to what we did in the last class. That's last class we were looking at absolute value, modulus of a number. So we have this problem. This problem is from the Kenyan Mathematics Competition 2001. This question was asked. The question goes thus: let A, B, and C be positive real numbers such that A plus B plus C is less than or equal to 4, and AB plus BC plus CA is greater than or equal to 4. Prove that at least two of the inequalities, absolute or modulus of A minus B is less than or equal to 2, modulus of B minus C less than or equal to 2, modulus of C minus A less than or equal to 2 are true. All right. So in this question, we are to prove that at least two means two or all three are true. Now, oftentimes in math, the issue is, yes, we've seen the facts, we read the question, we seem to understand it, but how do we move from here? How do we go about it? Okay, so this is a little hint of what you should do, which I didn't write out in my sheet. Now, the hint is that when you look at modulus A minus B, B minus C, C minus A, and you see you're given A, B, B, C, C, A, all right? Remember in algebra, we came across A plus B plus C all squared, and this AB plus BC plus CA is one of the terms we saw there. So what that means is that we would need to square this. So we need to have a mental picture of what we want to achieve. So we know that we're going to need to get to a point where we have A minus B all squared, B minus C all squared, C minus A all squared. So we need to analyze, work on what we have to take us to the point where we're going to have this square plus we're going to see a way out if we get there. Okay, so that is where our mind is. So we are thinking of how do we get to that point? How do we get to the point where we have A minus B all squared, B minus C all squared, C minus A all squared, possibly being added together. So we know our starting point is we're given A plus B plus C is less than or equal to 4. Now let me say this. So we square both sides, all right? Now let me say something here so that you're very careful. Now we are told that A, B, and C are positive real numbers. Now, this assumption is a very serious assumption. I'm going to show you why. Because if A and B and C are positive real numbers, it means A plus B plus C is a positive number. All right? It's a positive number. So if we square both sides, the inequality will still be intact. Now, this won't be the case if we weren't sure that A plus B plus C is or are positive numbers, or it gives us a positive number. It won't be the case. Let me give you an instance, all right? Now, we know that -5 is less than 4, all right? -5 is less than 4. Now, if you square both sides, -5 all squared becomes 25. Now, 4 squared is 16. Clearly, 25 is not less than 16. Are you seeing that? So squaring both sides for the inequality to remain, we need to be sure that the left-hand side is positive. So we are told in the question, A, B, and C are positive real numbers. So therefore, by squaring both sides, we are certain that the inequality sign will not change. All right, we are sure of the inequality sign. It remains. So it's very important because Olympiad problems, oftentimes you need to be very careful. You need to ensure you're working very closely with the facts given. You don't assume anything. You ensure that whatever you're doing is consistent with whatever you're told in the question. All right, so we squaring both sides, A plus B plus C all squared less than or equal to 4 squared. Now we have done this in our previous classes. We've expanded this. So A plus B plus C all squared gives us A squared plus B squared plus C squared plus 2 into AB, BC plus C less than or equal to 16. Now this is the inequality we have. Do not forget the mental picture we had initially. Okay, so we need to have A minus B all squared, B minus C all squared, C minus A all squared. Now if you think hard on this, you realize that, okay, let's say we're having all of them and they are being added together. So if you kind of square each of these and you add them together just to see what will result, because we are assuming, we are hoping that if we get to that point, we're going to see a way out. All right. Now, if you square a minus b all squared, b minus c all squared, c minus a all squared, if you don't expand, you would end up having 2a squared plus 2b squared plus 2c squared minus 2ab minus 2bc minus 2ca. All right. Now, that result of expansion, which is not on the solution here, I'm just showing you why we are doing what we're doing in our solution. All right. So we said, okay, the question says we should prove that at least 2 of the 3 are correct. Okay. Now we have done just one thing. We squared both sides and we have this. So we're thinking of, with this result we have and what we are given in the question, how do we move from here? How do we move from here? So we are saying, okay, let's square both sides. Okay, let's square each of these absolutes. Okay, in doing so, we've seen the terms that play out. So we want to play around what we have to see if we can get to that point. Now, one of the things I mentioned is that if you square, you're going to have 2a squared plus 2. So the next thing I did here was multiplying through by 2. So you multiply through by 2, you have 2a squared plus 2b squared plus 2c squared plus 2 times 2 is 4. So 4ab plus bc plus c equals the bracket is less than or equal to 32. All right. So this is almost like what we want. The only difference is that this should be minus 2. This should be minus 2 into ab plus bc plus c. That's really different. All right. So we put a hold on this. We call this inequality 1b. Now we take the other information, the other factor given in the question, which is ab plus bc plus ca is greater than or equal to 4. All right. So for this to be minus 2, it means we need to add negative 6 to it. So, okay. So what do? We multiply through by negative 6. So by multiplying through by negative 6, of course, everybody here has some basic exposure in inequality. And one of the things you should know is that inequalities are handled almost the same way equalities are handled, except for very few exceptions. One of such exceptions is that when you multiply both sides by a negative value, the inequality sign changes direction. Okay, so what happened here is that this is greater than or equal to, but because we're multiplying both sides by a negative value, it changes direction from greater than or equal to less than or equal to. All right, so this is 4 times negative 6, negative 24. Now we are adding this, we now call this inequality 2b. Now we're adding inequalities 1b and 2. So before you add 2 or more inequalities, you must ensure that the inequality signs are consistent. All right. So you see in inequality 1b, we have less than or equal to. Inequality 2b, we have less than or equal to. So the signs are consistent. They are the same. So we can add up. Okay. Left hand side will add to left, we interact with left hand side. Right hand side will interact with right hand side. And the results will still have the same inequality sign. It's very important you check for this thing. You don't just assume it. Before you interact 2 or 3 inequalities, that is adding or subtracting, you must ensure that the way you've written them out, the inequality signs are consistent. Having said that, so we're adding the 2, all right? That's why here we're adding the 2. We have 2a squared plus 2b squared plus 2c squared. There's nothing to interact with here. Now, ab plus bc plus ca, here we have 4 of it. Here we have negative 6 of it. So it's like saying 4x plus negative 6x, okay? So this is like saying 4x plus negative 6x. So 4x plus negative 6x is the same thing as 4x minus 6x, which is minus 2x. So we have minus 2x. X in this case is AB plus BC plus C. Okay? All right. Is less than or equal to 32 plus negative 24. We're moving to the right-hand side now. All right? So 32 plus negative 24 is the same as 32 minus 24, which gives us 8. Okay. Now, we have what we wanted. You know, remember we had in our question, we one of the things we tried was that, okay, let's what we're asked to prove, let's kind of square the left-hand side. Let's see what plays out, okay? So let's assume they are being added, all right? So that is what gave us the intuition to move in this direction. And so here we are. So we now separate it to be in the form of which obviously we square. So separating it, we have a squared minus 2ab plus b squared, all right? So if you open the bracket, you can pair them, a squared minus 2ab plus b squared, all right? B squared minus 2bc plus c squared minus 2ca plus a squared. Now, in case you're wondering how we did this. It's kind of simple. And if you open up the brackets here, this is going to become minus 2ab, minus 2bc, and minus 2ca. All right? So we can now group it. If you had done what I said, that is the question, what we're asked to prove, squaring each of them, you would understand how to group them now. All right? So we have grouped them. And in our grouping, now this is the same thing as now this is the same thing as a minus b all squared plus b minus c all squared plus c minus a all squared is less than or equal to 8. All right, is less than or equal to 8. So here we are. All right, so we need to think on this. Now, how do we move from here? The inequality 3. We know, all right, that the square of anything is at least 0. There is no negative number that can be expressed as a perfect square. There is none, as far as you're operating in the realms of real numbers. All right. If you choose to go into complex numbers, of course, you have there are lots of numbers that you can express as perfect squares. But as far as you're operating in real numbers, okay, real number system, there is no negative number that can be expressed as a perfect square. So in other words, the least value of a perfect square is 0. Okay, that's a question. That's information you should take seriously. So what we have here is that we have the sum of 3 perfect squares, because what is a perfect square? It's simply a number or an expression that can be expressed as a square of another number expression. Now we have 3. This is a perfect square. So we have the sum of 3 perfect squares, and their value is at most 8. At most 8 is the same thing as saying less than or equal to 8. Now let's think about this. Okay, let me just follow what I wrote here. So I say, note that if two or three of each of these terms is greater than 4, we'll have a result greater than 8. Of course, that is straightforward. All right. If 4 plus 4 is 8. All right. So if 2 of this is, let's say 2 of it is greater than 4, so the sum of those 2 that are greater than 4 will be greater than 8, and that cannot be possible because the third one, the right hand side, is saying at most 8. All right, so that means this contradicts the inequality 3. That's what I said, which is true. If you have on the left hand side 2, which add up to more than 8, of course it can be, because the right hand side is saying that the value of the left hand side is at most 8. Okay, so thus at most 1 can be greater than 4. Okay, oh we are saying at most 1 can be greater than 4. At most 1 can be greater than 4. Now, now this implies that now the opposite of greater than 4, okay, if something is not greater than 4, it is less than or equal to 4. All right, every number is either greater than 4 or less than or equal to 4. So if we've seen that at most 1 can be greater than 4, what's the opposite of that? The opposite is that the other 2, at least 2, is less than or equal to 4. So this implies that at least 2 of the expressions that are being summed up is less than or equal to 2. Less than or equal to 4. Okay, is less than or equal to 4. Now, this implies that at least, now, 4 is a perfect square, all right? 4 is a perfect square. So this implies that, and if you're saying a minus b, at least 2 of a minus b all squared, b minus c all squared, c minus a all squared is less than or equal to 4. Now, if we choose to jettison the square, all right, that means we're going to say that the modulus, because modulus is simply saying whatever is in the bracket will come out positive. That means the modulus of a, 2 of the modulus of a minus b, b minus c, c minus a is less than or equal to 2. So what we simply did was that we kind of took square root of both sides. So square root cancels out the 2, while square root of 4 is 2. So let me quickly summarize the problem. It's a warm-up problem. It's just, I saw it somewhere and I felt let's be a warm-up problem for today's class. Haven't done modulus in our last class. So what we are saying here is that we're just to prove that at most, or at least, 2 of these is less than or equal to 2. It is not sufficient to say it's obvious. In math, you must show that it is obvious. You don't say it is obvious. You show it's obvious. So what we started by doing was we square both sides, and sometimes in math you have to work backwards. So how do we get here? We say, okay, let's square each of this. We squared each of it. We added it up and it gave us something that looks like where my pointer is. All right. It gave us something like a squared minus 2ab plus b squared plus b squared minus 2bc plus c squared minus 2ca plus a squared. All right. When we added it up, it gave us something like the preceding line. So the plan was now to do our analysis to a point that we arrive at this expression. So that actually was the plan. And we played around the two inequalities we are given and eventually stumbled on it. Okay. So should in case you have any issue with this solution, feel free to contact me on WhatsApp to explain the aspects that you may be confused about. The time is fast spent. I spent too long here. So let's go to activities of today. I said we're looking at number theory today. So at the end of the class, you should be able to find number of divisors of a number. I won't go into the second one today because of time. I'll just stick with the first objective. If you want to find the number of divisors of a number. Funny enough, it sounds simple. All right, it sounds like I know this thing. Okay, so at the end of the class, you see whether you actually write about what you're saying in your mind or you're not. So let's quickly lay some foundation. So divisors of a number. So a divisor of a number n is a number that divides n. Okay, is that simple? All right, divisor of a number n is a number that. So we're saying n represents any number. All right. So divisor of a number n is a number that divides n. Okay, so a divisor of a number yields a remainder of 0 upon division. So what this point is saying is that whenever division goes on, there is always a remainder. That's what this point is saying. Whenever a division goes on, there's always a remainder. Now, if you say there's no remainder, there's actually a remainder, and that remainder is 0. Okay, remainder always exists whenever division is carried out. And we are saying that when the remainder is 0, it means that the number that divided is a divisor. All right, is a divisor. So we say a divisor is a number that uses a remainder of 0 upon division. It's very important because there are some problems. People forget that 0 is also a remainder. There are some problems that I think I may give you one of them in your assignment. If I find it, I'll include in your assignment. I've seen it somewhere. I'll include in your assignment so that you understand this point better. Now, a divisor of a number n is also a factor of the number n. Okay, some of you are very conversant with factors of a number. All right, that's maybe based on your country's mathematical curriculum, way of teaching. So what has been emphasized often is factors of a number, factors of a number. So factors of a number, same thing as divisors of the number. There's no difference. So when you talk about factor, talk about divisor. But in Olympiad terminology, we use the word factor divisor more often. We use the word divisor more often. Now, the number of divisors of a number n is denoted as tau of n. Tau of n. All right? The number of divisors of a number n is denoted as tau, as a tau of n. Now, it's very important you begin to note some of these Greek alphabet because we're using a lot of them in the course of our classes. Those of you that are science students, physics precisely, I think some of these Greek alphabets, you are conversant with some of them. So this is the first one. In the next number theory class, I'm going to introduce another Greek alphabet that denotes something in number theory. But for this class, tau, it looks like a T, stylish T you may like, but it's a Greek alphabet. It's not T. T is an English alphabet. So this is a Greek alphabet. So when you talk about number of divisors of a number, all right, it's like saying tau of that number. All right, tau of that number. Now, there is a formula for finding number of divisors of a number. And that's actually part of the bulk of this class is centered around that. All right. There is a formula for finding tau, finding number of divisors of a number. All right. The tau of a number. Don't forget I've said tau of a number is the same thing as what? Number of divisors of a number. So first of all, before we can find the tau of a number, we need to write a number as a prime in its prime decomposed form. All right, so we need to decompose our numbers into its prime. So we're given that n, let's say our number n is equal to p1 raised by a1 times p2 raised by a2 times ellipsis times pn raised by an. So what we're saying here is that you're expressing a number in, okay, the square of its prime factors, if you like. All right, so that's exactly what we're doing. So, but note that a1 is the powers of this prime, Okay, is the powers of this prime. So the tau of n is simply a1 plus 1 times a2 plus 1 times ellipsis times an plus 1. It's that simple. Now, let's see illustration so that we understand this better. Now, the divisors are, one will list the divisors of 12. So let's explain what the divisors of 12 are 1, 2, 3, 4, 6, and 12 is a small number, so it's very easy and possible for you to figure that out, the divisors of 12. So if you use to count your number, all right, that's the number. So one express 12, and you see is equal to 2 power 1. Now remember, let's go back to the previous one. The other power and we want to. That's the formula for tau of n. So that's the number of n powers 2, 1, 5, 2, 6, so the number works. So let's say that picture. Yes, 125. 125. 125 is the power of 5. So it divides 125 by 25. So of n. Okay, so 125 is the product of the prime factors. Incidentally, 125, 125 is one prime factor, which is 5. So the rule is one way to any. So oftentimes you hardly have to find to list the divisors of a number. You'll be asked to find the number of divisors a number has. All right, so you just simply use your tau function. Simply add 1 to the powers, keep multiplying, and you get your answer. Okay, now let's move on. When divided by number, interesting part here. There's so much to know. So divided by okay, all right. Okay, we have one basic one from our tau function, and that is just it. Now the next thing we want to note are very, very serious things. Very, very serious things. So first of all, tau of a number is simply a number of factors a number has, all right? Number of divisors a number has. So we said that given that B is a prime number, the tau of a prime number is always a prime number, all right? The tau of a prime number is tau of a prime number have just divisors and itself, okay? So the tau of a prime number is always 2, okay? Now, tau of Q is an odd number if and only if Q is a perfect square. Now, this word, if and only if, it's something very let me say this. If you say A if and only if B means 2 things, all right? Because some of us, you need to be conscious of in maths, we don't just write things anyhow. We must be logical. A if and only if B means 2 things. One is that it's saying if A, then B. It's also saying if B, then A. All right? Okay? Because oftentimes you'll be asked to prove A if and only if. If you have to prove an example, A to prove A if and only if B, it means you start off with 2 approaches. So you can prove one thing that's it. So that is, you're going to start with if A is true, you're going to prove that B is true. Then when you're done with that, you're going to proceed to prove if B is true, then you now show that A is true. Definitely, we would get to that point in the near future. So, but if the power of a number is an odd, if the result of a number, the result is odd, it means that the number we just computed, the tau of it, is a perfect square. The power of perfect squares is always odd. And if the result of the number is odd, the number is perfect square. Hello, someone say something?
No.
So that is it. We move on. And the product of all the values of n, now the product of n is equal to n raised to 2. The product of n is equal to n raised to the power of n by 2. If you find the product of a number, product of all the divisors of a number, all right? There is a formula for it. If you have to find the product of all the divisors of a number, all you need to do is to compute the power of that number. That is, you find number of divisors of that number, all right? Once you find the product of the product equal to n number of divisors by 2, okay? Now, the point I want to make that 10 is always at most 2 times the square root of n. It's always at most 2 times the square root of n. Let me get there. General things I'm mentioning will be proved. All these things I'm mentioning will be proved. All right. You don't just it will be proved, but in this class we'll just take the facts the way they are and use it in problem solving. In an advanced Olympiad class, it's not we would have to prove all these assertions I have written here. All right. Now the last one is that given n equal to, okay, that is a prime. Given an n equal to p1 raised by a1 times p2, okay, that is its prime decomposition, the prime decomposition of n. Now we are saying 2a1 plus 1 times 2a2 plus 1 ellipsis times 2an plus 1 is the number of ordered pairs of natural numbers. Is the number of ordered pairs of natural numbers AB with LCM equal to n. Now, okay, let's look at illustrations so that we understand this last point perfectly well. Now, 12 is equal to 2 raised power 2 times 3 raised power 1. Now we will now find all two ordered pair of numbers whose LCM is 12. We want to find two numbers, ordered pair. In case you confused about ordered pair, your mind should go to the Cartesian plane. All right, you're in your Cartesian plane. 2, 1 is not the same thing as 1, 2. All right, 2, 1 is the x coordinate is 2, y coordinate is 1, and that is not the same thing as saying x coordinate is 1, y coordinate is 2. So that's what ordered pair means. Ordered pair means that 5, 5, 3 is not the same thing as 3, 3, 5. It's not the same thing as 3, 3, 5. Okay, so now I want to find the pair of two numbers, ordered pair, such that the LCM is 12. Okay, the LCM is 12. Now, we know that 12 can be one of that number and it can combine with any of the factors of 12. All right, 12 can be one of that number and it can be combined with any of the factors of 12. So we have 1, 12, 2, 12, 3, 12, 4, 12, 6, 12, 12, 12. Okay, now because we are saying ordered pair, 6, 12 and 12, 6 are two different pairs. Now 12, 12 is just, we can't repeat this. So you observe that we started repeating it. 1, 12, we also have 12, 1, 12, 2, 12, 3, 12, 4, 12, 6 as well up to this point. Okay, so far we've listed all the pairs that has to do with 12. Now we move on to numbers, pairs that has 12 is not present, okay? And if you think about this, okay, if you think about this, you see you have 4, 6, you have 6, 4, 3, 4, and 4, 3. Now, if you want to count them, there are 15 of them. Now, the problem with this method is that we all, the of making a mistake is very high. And that's why if they ask you to find all two other pairs of numbers whose LCM is 12, it is not wise to go about listing them. Okay? It's better if we know some formula that we could use to get our result. And in the last slide, we established that formula. We said given n is equal to P1 raised by A1 times P2 raised by A2 times ellipsis Pn raised by An, that's 2A1 plus 1 times 2A2 plus 1 ellipsis times 2AN plus 1 is the number of ordered pairs of natural numbers AB with LCM of AB equal to 12. So in the context of this question, our n is 12. Our n is 12, and we want to find the number of ordered pairs. So simply, we see the powers here, 2 and 1. That's just the powers, 2 and 1. So we plug it in. So this is what? 2 times 2 plus 1 times 2 times 1 plus 1. And if you simplify this, you would see that you will get 15. You will get 15. Okay? Okay, I hope you got that. Now we move on to the next work example. Now this is how you see it in Olympiad. It always comes in a form that if you do not apply the formula, you would unlikely get the answer right. You unlikely get the answer right. Now this is a problem. Determine the number of ordered pairs of positive integers a, b such that the least common multiple, some of you know it as lowest common multiple, LCM, it means the same thing, of a and b is 2 raised to the power 3 times 3 raised to the power 5 times 5 raised to the power 7. All right? All we need to do is to apply a formula. A formula simply says 2 times the power plus 1 times 2 times another power plus 1. And we keep going until we exhaust all the powers present. So the powers we have are what? 3, 5, and 7. So we have 2 times 3 plus 1 times 2 times 5 plus 1 times 2 times 7 plus 1. And this is 7 times what? 11 times 15. And if you simplify that, you're going to have 1,155. Obviously, it wouldn't have been possible for you to list out all of them. Okay? So that's why you should take that formula very seriously. Please note what each formula is for so that you don't mix it up when the need arises. Now, this is another interesting maths problem. It's an interesting maths problem. Okay, so I'm going to ensure I think I have some time. So let me take time to explain this so that you understand. We asked how many positive divisors of 10 raised to the power 99 is an integer multiple of 10 raised to the power 88. Okay, it's a question that you need to think about carefully. So asking how many divisors of 10 raised to the power 99 multiple of 10 raised to the power 88. Now, let's establish some facts which may not have taken note of before. That the lower powers of a number are factors or divisors of that number. Okay, this is what I mean. If I have 2 raised to the power 100, okay, 2 raised to the power 100, now every lower power of 2 raised to the power, or every lower power of 2 is a divisor of 2 raised to the power 100. So for 2 raised to the power 100, 2 raised to the power 9 is a divisor, 2 raised to the power 8 is a divisor, 2 raised to the power 50 is a divisor, 2 raised to the power 10 is a divisor. Okay, so that is something we know about. Now let's speak more about a divisor is a number that divides without element. Okay, now another way we're looking at this concept of a divisor is that a divisor is a number that can multiply another integer to give that number. Okay? A divisor is a number that can multiply another integer to give that number. So if we look at 2 raised to the power 100, now any number less than 100, let's say 95 for instance, 2 raised to the power 100, the same thing as 2 raised to the power 95 plus 5. And by laws of indices, we have 2 raised to the power 95 times 2 raised to the power 5. Okay, so clearly you see that 2 raised to the power 95 multiplies another integer to give 2 raised to the power 100. So therefore, 2 raised to the power 95 is a divisor, is a factor. All right. So it's very important you understand these things before you do this problem. But that is the ideas that I brought to bear in solutions. Okay. The lower powers of a number are divisors of that. Okay. Now let's solve a problem. Now in our problem we see that we have to find number of positive divisors of 10 raised to the power 99. In other words, the starting point is divisors of 10 raised to the power 99. That's the point. Divisors of 10 raised to the power 99. So we have to find divisors of 10 raised to the power 99. But not just all the divisors, not just any divisor. Now these divisors must be an multiple of 10 raised to the power 88. In other words, these divisors must be one greater than 10 raised to the power 8, because every number that is a multiple of a number is greater than or equal to that number. All right, is greater than or equal to that number. So 10 raised to the power 88, a multiple. Okay, let's start. We're asked to find how many divisors of 10 raised to the power 99. How many divisors of 10 raised to the power 99? So we're looking at numbers. Divisors of a numbers are less than or equal to that number. Divisors of a number are less than or equal to that number. So we have to find how many positive divisors of 10 raised to the power 99 is an integer multiple of 10 raised to the power 88. In other words, these divisors of 10 raised to the power 99 must be at least 10 raised to the power 88. Okay, so we see that there is a range of values for our numbers. Our numbers must be greater than or equal to 10 raised to the power 88. Our numbers must be less than or equal to 10 raised to the power 99. So that's exactly where we find all our numbers. Now, even at that, there are many paths that one could move from there. There are many ways, many approaches that one could choose to take from there. Okay, but I choose a particular method I feel that it's going to be easy for us to understand. So I started off by saying 10 raised to the power 99 is equal to 10 raised to the power 88 times 10 raised to the power 11. Clearly, this is true from law of indices. Apply on the right-hand side. We know that when the bases are the same and multiplication is an operation, we add the powers. All right, we add the powers. So 88 plus 11 will give us 99. We add the powers. All right. So that's the first step. So this is true. Now we need to now see how do we move from here. Now, when you're looking at divisors of 10 raised to the power 99, so we're interested in every number, okay, that 10 raised to the power 88 will multiply to, and we give 10 raised to the power 99. That's one, and its similitude. So I said, thus, our required number is the same as the number of divisors of 10 raised to the power 11. I want to explain why this is so. Now, the left side, please listen. From the constraint of our question, we know that our number must be at least 10 raised to the power 88. Okay? Our number must be at least 10 raised to the power 88. Our numbers cannot be greater than 10 raised to the power 99. Okay? Now, 10 raised to the power 99 is equal to 10 raised to the power 88 times 10 raised to the power 11. So we need all our answers must be at least 10 raised to the power 88. So the question now is 10 raised to the power 11. In how many ways can we express how many factors How many divisors does 10 raised by 11 have? Now, when you identify these divisors, we know that the divisors we require in our question is simply 10 raised by 88 times each of these divisors. Of course, one of the divisors of 10 raised by 11 is 1. So 1 times 10 raised by 88, it satisfies the constraint of our question. Another divisor is 2. So 2 times it satisfies the constraint of our question. So by so interacting, we end up getting the number of divisors we'll get at the end of the day is the same as the number of divisors of 10 raised by 11. Okay? All right. So that's why I say our question is the same thing as saying the number of divisors of 10 raised by 11. So we want to find the number of divisors of 10 raised by 11. So it's the same thing as saying find the tau of 10 raised by 11. Finding the tau of 10 raised by 11. Now, 10 raised by 11 is 2 raised by 11 because we said before you find the tau of a number, you must express it as its prime decomposed form. Prime decomposed form. So we have that 10 raised by 11 is the same thing as, of course, 10 is 2 times 5. This is again laws of indices. All right. It's not difficult to see that 10 raised by 11 is equal to 2 raised by 11 times 5 raised by 11. Okay, 10 raised by 11 is the same thing as what? 2 raised by 11 times 5 raised by 11. So one will find a tau of 10 raised by 11. So you simply take the powers, we add 1 to it and multiply. So that's 11 plus 1, 11 plus 1, 144. So what was 144? 10 raised by 11 here has 144 factors. And when each of these factors multiply 10 raised by 88, the constraint of the question is satisfied. Don't forget the constraint of the question is that the divisors we're interested in, okay, number one, they must be divisors of 10 raised by 99. That's number one. Now, number two, these numbers are greater than 10 raised by 88. In fact, are multiples of 10 raised by 88. All right? And at the same time, they are less than 10 raised by 99. So when you get all the divisors of 10 raised by 11, when you multiply each of them to 10 raised by 88, the constraint of the question is satisfied. Yes, Mohammed, let me hear you.
So why do we sum up 11 and 1?
Okay, it's so at this point, do you understand up to the point where I said our required answer is the same thing as the number of divisors of 10 raised by 11?
Yes.
Okay, now what is the formula for finding number of divisors of a number? We'd established it in the previous slide. Let me find it. Where is it? Okay, I think this is it. I just passed it. So see it here, the last point. Now, given that n is equal to this, the tau of n, which is the same thing. Okay, no, this is not it. This is something else. Okay, the tau of n, which is the same thing as number of divisors of n, is simply, you see, each of the powers, we add 1 to it and we're multiplying. Are you seeing that?
Yes.
So it is this formula we applied there. All right, is this formula we applied there? Okay, so the powers, yeah, 11 and 11. So we add 1 to it and multiply and we go 144. I hope you're okay.
Yes.
Okay. We have okay, we have some time. So we now move on to the next example, which I think is the last example for today's class. Now we have to find determine the product of all distinct natural numbers divisors of 200 raised power 4. Okay. We have to determine the product of all distinct. Note the word distinct means different. Natural number divisors of 200 raised power 4. So simply, we just apply the formula we've learned. We've learned some. I'm going to still go through. After this example, I'll still go through the important points I've made in the course of this class, which you should retain, because you're going to find Olympiad math problems that those ideas, those methods will need to be applied to get the correct answer. So we have to find the number of product of all distinct natural number divisors of 200 raised power 4. Trust me, If you list the divisors, it's going to take you a very long time. Although those of you that are very smart, there's a way you could actually find these if without even knowing the formula. Of course, in life, there's more than one route to a thing. There are more than one method to use to solve a problem. All right. So, but I'm going to use the one I've emphasized in the class so far. So, for us to find the product of all distinct natural numbers, divisors of 200 raised to the power 4. Yes, Ibrahim. You want to ask a question?
No, sir.
Okay. So number of product of all divisors of n is simply, so we need to first of all express 200 raised to the power 4 as a product of its prime factors. Okay. We have to decompose it into its into prime factors. So we have 200 raised to the power 4. If you do it, you have 2 raised to the power 12 times 5 raised to the power 8. How do you go about this? I believe you should know. There's a law of indices that says a times b all raised to the power n. Okay, you have a times b in a bracket, all raised to the power n is the same thing as a raised to the power n times b raised to the power n. So if you know that law, you can. It's very easy to move. 200 we know is 8 times 200 is 8 times 10, 8 times 25. Okay, 200 is 8 times 25. Okay, 208 times 25. So 200 raised to the power 4 is the same thing as what? 8 raised to the power 4 times 25 raised to the power 4. So, and the rest is simple. Of course, you know that 25 raised to the power 4 is the same thing as 5 raised to the power 8. While 8 raised to the power 4, same thing as 2 raised to the power 12. So the issue here is that I believe that's not an issue. That's why I didn't do it here. The important thing is that 200 raised to the power 4 is the same thing as 2 raised to the power 12 times 5 raised to the power 8. 2 raised to the power 12 times 5 raised to the power 8. Now, we're interested in the power of 200 raised to the power 4. And the idea is simple. Once you express the number as a product of its prime factors, you simply 12 plus 1 times 8 plus 1, and we have 117. So what does this mean? 200 raised to the power 4, there are 117 of them. There are 117 numbers that are divisors. So we need that information. Now, back to the question. The question is asking us to find the product of all distinct natural numbers. All distinct natural number divisors of 200 raised to the power 4. That is, you don't just find the divisors, you multiply them together. Okay? You find, after finding all the divisors, all the positive divisors, you then multiply all of them together. What would the result be? And we've established that the product of all divisors is equal to of n divided by 2. We've established this result. That is the formula. So our desired answer will be, when in this case, 4. And 2. And then we apply the power rule. What does power rule say? When a base raised to a power and the whole expression is raised to another power, okay, it is the same as the base raised to the product of 2 powers. So 200 raised to the power 4, or raised to the power 117 times 2, okay, is the same thing as, of course, 2 would cancel for 2. 2 times 117, we have 134. So what I'm saying in essence, 200 divided by 2 plus 200 raised to the power 200. Now, let me go back to the very beginning and emphasize the thing that you must know. At the beginning of this class, we said that we have just one objective, and that you should be able to find the number of divisors, the number of divisors. And I said, I won't go to some of the divisors. We'll just look at numbers. In a subsequent number theory class, we will look at some divisors numbers and more like numbers here. So many. For today, our focus was on the number of divisors of a number. That was our focus. The number of divisors of a number. And we said, to find the number of divisors of a number, you need to decompose the number in its prime as a product of its prime. Okay? You need to decompose the number as a product of its prime. So when you do that, each prime number would have a power. To have a power. Each prime number will have a power. So the number of divisors of the number is equal to, you add 1 to each of these powers and multiply it together. Now we've established that the number of divisors of the number is a tau of that number. Okay? Tau is a Greek alphabet. Okay? Tau, it looks like T, but not T. The tau of a number. That's the number of divisors of a number. So having decomposed your number into the product of its primes, you identify the powers of your primes. And we want to wait as many as you have. So that's the first important result established. Okay? That to find the number of divisors of a number, which is simply as a tau of a number, you decompose the number into a product of its primes. Once you've done that, identify the powers of the primes. And once you identify the powers of the primes, the next thing you do is that you add 1 to it, add 1 to it, and multiply, and you get the result. Okay, you get the result. Now, the next thing we established was that the important part to establish is that given a prime number, the tau of a prime number will always be 2. So you could be asking an inductive question. These things come out in some Olympiad problems. As in, they say, given that a tau of a number is equal to 2, what is the number? The number is obviously what? Prime number. In fact, someone could ask you, tau of x is equal to 2. Which of these is a possible value of 2? And the person puts there 4, 5, 6, 7, 8. Now, without having to spend too much time on it, you just look for which one is prime. 7 is prime, so therefore 7 is the answer. Because for the rest, the tau would obviously be greater than 2. So that's another thing. Tau of every composite number. You know, for every number greater than 1, is either it's a prime number or it's a composite number. That's the opposite. So we see that the tau of every composite number is greater than 2. There is no number you think of that is composite, that is not prime, that the tau of it is less than or equal to 2. So these are important facts you should know, because Olympiad problems are very amazing. They could just build a whole problem based on this little fact. Now, we also established that if you find the tau of a number and you have an odd number, it means that that number you found a tau of is a perfect square. All right? So taus of perfect squares are always odd number. If an odd number result, it means the number is what? Perfect square. All right? Perfect square. So if you have an address question, they say tau of x is equal to 343. Okay, what is x? And you have a list of numbers, and you quickly go through. You see all of them are even except one. All of them, only one perfect square is amongst them. The rest are not perfect square. Just know that that one which is a perfect square is the answer, because it's only a perfect square that the tau of it can be odd. And the last two results we established is that the product of all divisors of n, okay, let's say you have all the divisors and you multiply all the divisors, the result will always be equal to n raised to the tau of that number divided by 2. And I said, this is the general purpose class. There's certain things I don't do here, but in an advanced Olympiad training, I won't just state this fact, I will prove them, because in math, everything is provable. Everything is proved. We don't just say things and swallow, we prove them. But I think stating this serves the purpose of this class. All right, serves the purpose of this class. So it's n raised to tau of n divided by 2. And the last important result we should take seriously is that given a number n, if we're interested in ordered pairs of two natural numbers whose LCM is n, the number of such pairs is simply 2a1 plus 1 times 2a2 plus 1 ellipses times 2an plus 1. Okay, so those are the important facts I have established in this class. It's time. I don't want to go beyond the time. So it was nice having you around. Again, a good number of you are fond of not sending in your assignments. In the near future, you may not get links to this class, because very soon those that will be getting links to the class are those that have been actively involved. And what I mean by actively involved means persons that turn in the assignments. Okay, so I want to advise you, you're going to get these notes in 1 hour time, 1 or 2 hours time. You're going to get the notes. Once you get it, endeavor to do your assignment and send it to me. All right, so we'll meet again same time next week. If you have any issues, feel free to contact me on WhatsApp for me to give you further clarification. So have a lovely weekend.